Hi! In the last video, we've introduced the first and the second properties that are related to R2pi, C, and phi. And in this video, we will continue on this section, and after that, we are ready to introduce the convergence of Fourier series. So let's first talk about the second property. If f is inside R2pi and it is k times differentiable such that the kth derivative is inside R2pi, then we have the head of the kth derivative of f of n is equal to in to the power k and times f hat n. And we are going to prove it. Well, it's the fastest to prove that the head of f prime n is equal to in times f hat n, because it can be extended by mathematical induction. So let g be a differentiable function such that g and g prime are inside R2pi. And we're going to compute the integral from negative pi to pi g prime x times cosine nx, and it is equal to the integral from negative pi to pi of cosine nx dgx. Using the integration by part, we see that it is equal to cosine n pi g pi minus cosine n pi g negative pi plus n times the integral from negative pi to pi gx sine x. And notice cosine n pi is equal to cosine negative n pi, so we can factor the term cosine n pi out, and we get that it is equal to cosine n pi times g pi minus g negative pi. Well, notice something. G is 2pi periodic, so we see that it is the g negative pi should be equal to g pi. Therefore, this term will vanish, and we are left with the term n times the integral from negative pi to pi cosine x sine x. So we get this formula. And similarly, using the fact that sine n pi is equal to 0 for all n which is an integer, we have the integral from negative pi to pi g prime x sine nx is equal to negative n times the integral from negative pi to pi gx cosine nx. So if we write f equal to f1 plus I f2, we get that the head of f prime of n should be equal to 1 over 2 pi times the integral from negative pi to pi f1 prime plus I f2 prime times cosine nx minus sine nx. And after we expand these two complex number and we divide it into real parts and imaginary parts, we get that it is equal to such expression. And remember, if we want to remove the prime here, we have to multiply both sides by n. And if we are facing sine nx, then we will take a negative. So such expression become the next line. And recognize something. If we get a term I from this factor, we will recover the term f hat n. And if you don't understand why, you can just expand the term f hat n, and you will see the same thing when I take out the term I from this expression. Thus, we get that it is equal to in times f hat n. And this is a very amazing property. It's because before we haven't investigated this property, we may find that the finding Fourier series for the kth derivative of f may be difficult. But now, the task becomes very easy. We can just multiply the Fourier coefficient of f by the term in to the kth power, and we can obtain the Fourier coefficient of f to the k derivative, and we can get the Fourier series of f to the k derivative very easily. So the next is the property 3, and we let f(ax) be fx plus a, and indeed this is just a translation, and we claim that f hat of a of n should be equal to e to the I n a times f hat n, and well, this is very easy to prove, and therefore I will leave it as an exercise. We have talked about the properties that are related to R2pi, C, and phi. We are ready to investigate the convergence of Fourier series. So let's recall the property 2 that we have just proved. We have proved that the head of f to the kth derivative of n is equal to in to the kth power times f hat n. And also, we also recall that all integrable functions are bounded. So we get that the absolute value of f hat n should be equal to the head of the second derivative of f of n over n squared. And according to the definition of the head of f to the second derivative, this is equal to 1 over 2 pi times the absolute value of the integral from negative pi to pi of the second derivative of f times e to the negative inx, and we put the absolute sign from the outside to inside. This equal sign become a small than or equal to, and therefore we get that it is smaller than or equal to 1 over 2 pi times the integral from negative pi to pi of the absolute value of the second derivative of fx over n squared. And notice something, that the absolute value of this thing should be 1, and it is because of the Euler's formula only. And notice something, we have just claimed something that all integrable functions should be bounded. So this term is bounded. So if we let m to be the maximum of f to the second derivative inside the closed interval negative pi to pi, we get that it is smaller than or equal to 1 over 2 pi times the integral from negative pi to pi of m and over n squared. And this is just a constant function, so we can simply compute its integral, and we get that this integral is equal to m times 2 pi. And therefore, the 2 pi here and here cancel out, and we are left with m over n squared. And remember that the sum of 1 over n squared from 1 to infinity converges. So by the Weierstrass M test, the Fourier series converges. So as a conclusion, we have the following theorem. The following theorem says that if f is a twice differentiable function such that f, the second derivative, is inside R2pi, then the Fourier series of f converges. And this is the end about the convergence of the Fourier series of a function. And in the next video, we will investigate the convergence of Fourier series of f to the function itself. And it is because sometimes the Fourier series of f may not converge to f itself. And we will see some examples in the next video, and we will find out how we can investigate such problem. See you in the next video.